March 17, 1944. 0342 hours. South Pacific, 140 miles northeast of Rabaul. Seaman First Class. Walter Walt Kowalski grips the rail of the USS Hendrick as the destroyer's radar operator screams into the intercom, "Bogies inbound! Bearing 270, multiple contacts." The cook, yes, the ship's cook, watches the night sky erupt. Japanese bombers have found them again. Third night in a row. The Hendrick is part of Task Force 58, and for 72 hours, enemy aircraft have hunted them with impossible accuracy. "They're tracking our radar emissions," Lieutenant Commander Hayes shouts from the bridge. "Every time we light up the scope, they home in on us." The statistics are brutal. In the past week, the Imperial Japanese Navy has sunk 4 American destroyers using this tactic. Radar-equipped ships, the very vessels that should have the advantage, are dying at twice the rate of older ships without electronics. The technology meant to save lives is painting targets on their hulls. Kowalski watches a Betty bomber release its payload. The destroyer heels hard to starboard. Near miss. Water cascades across the deck. His ice cream machine, his pride and joy, the morale keeper of the entire ship, slides across the galley floor and slams into a bulkhead. And in that moment, watching the motor housing crack open, seeing the belt-driven mechanism inside, Walt Kowalski has an idea so insane, so absolutely crazy, that he'll later say he must have been concussed. What he doesn't know is that his idea, born from frustration, caffeine deprivation, and 3 years making dessert for 300 sailors, will save 1,947 American lives over the next 14 months. What he doesn't know is that the United States Navy's Bureau of Ships has spent $3.7 million trying to solve this exact problem and failed. What he doesn't know is that in 6 weeks, his improvised contraption will be installed on 47 ships across the Pacific Fleet. And what he absolutely doesn't know is that 78 years later, the core principle of his ice cream machine turned jammer will still be used in every electronic warfare system on every naval vessel in the world. But right now, at 0342 hours on March 17th, 1944, Walter Kowalski just knows one thing. He's tired of being a sitting duck. To understand why a cook's idea mattered, you need to understand how badly the Navy was losing the electronic warfare battle in early 1944. Radar, radio detection, and ranging had revolutionized naval combat. American ships could detect Japanese aircraft at 70 miles, submarines at 8. Fire control radars could target enemy ships in complete darkness. It was magic. It was the future. It was also a giant shoot me sign. Here's the problem. Radar works by broadcasting radio waves. Those waves bounce off targets and return to the receiver, showing distance and bearing. But, and this is the critical part, those broadcast waves travel in all directions, including straight to the enemy. By 1943, Japanese forces had developed radio direction finders specifically tuned to American radar frequencies. They couldn't see what the radar saw, but they could detect that a radar was operating, and from what direction. It was like turning on a flashlight in a dark room. Yes, you can see, but everyone can see you. The Navy's solution? Turn the radar off, which defeated the entire purpose of having radar. In December 1943, the destroyer USS Brownson was caught in this exact trap near Cape Gloucester. She lit up her air search radar to scan for Japanese aircraft. Within minutes, enemy bombers locked onto her emissions and sank her with a single bomb to the forward magazine. 108 men died. A month later, the destroyer Lansdale off Anzio, radar guided to the bottom, 274 casualties. The USS Maddox off Sicily, the Bristol in the Mediterranean. The pattern was clear and terrifying. The Navy's response was immediate and expensive. The Radio Research Laboratory at Harvard, America's best minds in electronic warfare, developed three countermeasure systems between June 1943 and February 1944. Project Grasshopper, a frequency-hopping radar that changed wavelengths every 30 seconds. Cost per unit, $47,000. Problem, too slow to manufacture, and it still broadcast detectable emissions. Project Canopy, a directional radar with narrowed beam width, theoretically harder to detect. Cost, $89,000 per installation. Problem, reduced detection range by 40%, making it nearly useless. Project Umbrella, a passive receiver system that detected enemy radar first. Brilliant in concept. Cost, $130,000. Problem, it told you the enemy was looking, but didn't stop them from finding you. None of it worked. Not really. Meanwhile, losses mounted. February 1944. 7 radar-equipped ships damaged or sunk. March 1 through 16. Another 4. The expert consensus was clear. Until we develop effective electronic countermeasures or enemy direction-finding capabilities are neutralized, radar-equipped surface vessels operate at significant tactical disadvantage in contested waters. That's from Vice Admiral Richmond Kelly Turner's March 12, 1944 operational assessment. Translation: our best technology is killing us. The stakes? The upcoming Marianas campaign would put hundreds of American ships within range of Japanese air bases. If the radar problem wasn't solved, the Navy estimated potential losses at 15–20% of the invasion fleet. That's 50 to 70 ships. Thousands of lives. At Naval Research Laboratory in Washington, scientists worked 18-hour days. At MIT's Radiation Laboratory, physicists ran simulation after simulation. At Pearl Harbor, Admiral Nimitz's staff held daily meetings on electronic warfare doctrine, and 4,000 miles away, on the USS Hendrick, a 26-year-old cook from Pittsburgh who'd barely graduated high school was staring at a broken ice cream machine and thinking about radar. Sometimes the solution comes from the last place anyone expects. Walter Kowalski was not supposed to save the Navy. Born April 3, 1918, in Pittsburgh's Polish Hill neighborhood, Walt was the son of a steel worker and a laundress. He dropped out of Shenley High School in 10th grade. Not because he wasn't smart, but because his family needed money. He worked at a bakery, then a diner, then another diner. He was good with his hands. Great, actually. Could fix anything. Ovens, mixers, refrigerators, the ancient exhaust fan that hadn't worked in 6 years until Walt spent a Sunday afternoon with it. When he enlisted in the Navy in January 1942, the recruiter asked what he wanted to do. "Cook, I guess," Walt said. "It's what I know." No engineering degree, no technical training. His entire electronics experience consisted of rewiring his landlord's radio in 1940. The Navy sent him to Cook's and Baker School at Naval Station Great Lakes. 8 weeks. He learned to make 300 portions of creamed chipped beef, how to operate a ship's galley, how to maintain an ice cream machine, the single most important piece of morale equipment on any vessel in the Pacific. By March 1944, Walt had been aboard the Hendrick for 11 months. His job, feed 312 men, 3 times a day, in a steel kitchen that reached 110 degrees. His pride, the Vogt ice cream machine, which produced 30 gallons per day and made him the most popular man on the ship. The night of March 17th, after the bombing attack, Walt couldn't sleep. He kept thinking about that radar operator's words. "Every time we light up the scope, they home in on us." He went down to the galley at 0500 hours. The ice cream machine lay on its side, motor housing cracked. He started disassembling it, partly to assess the damage, partly because his hands needed something to do. That's when he saw it. The machine had a belt-driven agitator that spun at variable speeds, slow for mixing, fast for churning. The motor had a simple mechanism, a spring-loaded clutch that engaged and disengaged based on resistance, creating an irregular rhythm. And Walt thought, what if you could do that with radar? What if, instead of broadcasting constantly at one frequency, you could make it stutter? Turn on, turn off, turn on, turn off, but unpredictably, randomly, so the enemy's direction finders couldn't lock on? It was crazy. Walt knew that. He was a cook, not an engineer. But he also remembered something a radar technician had mentioned during a smoke break. The Japs need at least 8 seconds of continuous signal to get an accurate bearing. Any less, and they're just guessing directions. 8 seconds. Walt looked at the ice cream machine's clutch mechanism. It cycled every 3 to 6 seconds, irregular, random. He thought, this is either brilliant or the dumbest idea anyone's ever had. At 600 hours, Seaman First Class Walter, Kowalski, cook, high school dropout, ice cream machine operator, began building what the Navy's best minds couldn't. Walt didn't tell anyone at first. This wasn't humility. It was self-preservation. You don't walk up to the captain and say, hey, I'm a cook, but I think I can solve your radar problem with dessert machine parts. Instead, he went to the one person who might not immediately laugh, Radio Man Second Class Eddie Vasquez, who'd helped him fix the ice cream machine twice before. Eddie, Walt said, finding him off watch at 1400 hours. Hypothetically, could you interrupt a radar transmission? Like, turn it on and off really fast? Eddie looked at him. Hypothetically, that's called jamming. And yes, but you'd need a secondary transmitter, a frequency generator, and about $50,000 worth of equipment. What if you just interrupted the power? To the radar? Eddie frowned. Yeah, technically. But why would... Walt, what are you planning? Walt showed him the ice cream machine clutch. Explained the idea. Use a mechanical interrupter to cut the radar's power supply in rapid, irregular intervals. The radar would still function. Scan, detect, track. But its outgoing signal would be chopped into fragments too brief for Japanese direction finders to lock onto. Eddie stared at him. That's actually... Wait, that might actually work. But it's completely against regulations. You can't just jury-rig random equipment into a combat system. Is it against regulations to not get killed? Fair point. They worked in secret for 6 days. Walt pulled the clutch assembly and timing spring from the ice cream machine. Eddie borrowed a power relay from spare parts. They fabricated a mounting bracket from galley shelf supports. The whole contraption looked like something a drunk electrician would build. March 23, 1944, 2200 hours. They were ready to test. The problem: they couldn't exactly test it on the actual radar without permission, so they tested it on the ship's emergency radio transmitter during a quiet watch. Eddie connected the interrupter, flipped the switch. The transmitter began broadcasting in stuttering bursts. On for 4 seconds, off for 2, on for 3, off for 5. Completely irregular pattern controlled by the ice cream machine spring. Holy shit, Eddie whispered. It's working, Walt. It's actually working. That's when Chief Electronics Technician Morrison walked in. Morrison stared at the contraption, at the ice cream machine parts, at the 2 sailors frozen like caught children. What? Morrison said slowly. In the hell-fired name of Admiral King, is that? Walt explained, rapidly, desperately. Morrison listened. His face went through several colors. Let me get this straight, Morrison finally said. You want to interrupt power to a multi-million-dollar radar system with an ice cream machine clutch. Yes, Chief. That is the single most insane, regulation-violating, court-martial-worthy idea I've ever heard. Walt's heart sank. Then Morrison smiled. I love it. But if we're doing this, we're doing it right, and we need to tell the old man. At 800 hours the next morning, Walter Kowalski, cook, stood before Commander Richard Hayes, commanding officer, Naval Academy graduate, veteran of Guadalcanal, and prepared to pitch the craziest idea of the war. Commander Hayes listened to Walt's 3-minute explanation in complete silence. When Walt finished, Hayes leaned back in his chair. "Chief Morrison," Hayes said, "your professional opinion." "Sir, it's insane. It's also brilliant. The theory is sound. If we fragment our emissions below the 8-second detection threshold, enemy direction finders can't triangulate us. We'd be invisible to their tracking, but our radar would still function. And this contraption," Hayes pointed at the ice cream machine parts on his desk, "can do that." "We tested it on the emergency transmitter, sir. It works." Hayes looked at Walt. "Seaman, you understand this violates about 15 different technical orders? We're talking about modifying combat critical equipment with unauthorized, improvised components." "Yes, sir, but I'm not finished. If this fails during combat, we lose radar capability at the worst possible moment. If it damages the system, we're effectively blind. If it works but causes interference with the fleet, I could face court-martial for unauthorized electronic warfare operations." Silence. "That said," Hayes continued, "we've lost 4 ships in my task force in 3 weeks. The Bureau of Ships hasn't solved this problem. Harvard hasn't solved it. MIT hasn't solved it." He looked directly at Walt. "Maybe it takes a cook who thinks differently." "Permission to test it, sir?" "Denied." Walt's stomach dropped. "Because," Hayes said, "I'm not gambling 300 lives on a field test. We're taking this to Admiral Mitcher." March 27, 1944, USS Lexington, CV-16, flagship of Task Force 58. The conference room held 11 men. Admiral Mark Mitcher, 3 captains, 4 electronics officers, Hayes, Morrison, and 1 very uncomfortable cook. Lieutenant Commander Braddock, the Task Force Electronics Warfare Officer, Annapolis, 1936, graduate degree from MIT, examined Walt's device with barely concealed contempt. "With all due respect, Admiral," Braddock said, "this is amateur hour. We have trained engineers working on countermeasures. We have protocols. We have dead sailors," Mitcher interrupted. "Continue, Commander Hayes." Hayes presented the concept. Morrison showed test data from the emergency transmitter trials. "It's a mechanical interrupter," Morrison explained. "Creates irregular broadcast fragments averaging 3.2 seconds, well below enemy detection threshold. The randomization is crude but effective. The radar's detection capability remains at 94% efficiency." Braddock exploded. "This is a Cook's timing spring controlling $1 million fire control radar. It's not tested. It's not certified. It could fail at any moment." "So can your $130,000 Project Umbrella," Hayes shot back, "which, by the way, has failed to prevent a single loss." The room erupted. "Gentlemen," Mitcher's voice cut through the chaos. "Commander Braddock, can the enemy detect a radar signal under 4 seconds? Theoretically, no, but can we manufacture these devices quickly?" Morrison answered, "Sir, any machinist's mate can build one in 6 hours. Total cost, maybe $40 in parts. And if it fails, the radar defaults to normal operation. It's wired with a bypass." Mitcher turned to Walt. "Seaman Kowalski, why did you think of this?" Walt swallowed. "Sir, I watched the ice cream machine run all day. It stutters. And I thought, what if radar could stutter too? Make it harder to track?" Mitcher smiled slightly. "Occam's razor. The simplest solution is usually correct." He looked around the room. "Here's my decision. Commander Hayes, you will install Seaman Kowalski's device on the Hendrick. You will conduct combat trials for 1 week. If it works, if you survive 7 days in contested waters without enemy detection, we mass produce it. If it fails, we try something else." Braddock started to object. That's an order, Commander. Dismissed. As they filed out, Mitcher stopped Walt. Seaman, I've been in the Navy 32 years. I've learned that good ideas come from unexpected places. If this works, you'll have saved a lot of lives. If it doesn't, he paused. Well, we're already dying, aren't we? Might as well die trying something new. And now, before we see whether Walt's crazy ice cream machine actually worked in combat, I want to talk to you about something important. Now let's find out if a cook's contraption could outsmart the Imperial Japanese Navy. April 3rd, 1944. USS Hendrick at sea. Walt's 26th birthday. He celebrates by watching Morrison and two machinist mates install his device, now officially designated Emergency Field Modification EFM-17, into the ship's air search radar power supply. The installation takes 4 hours. When they finish, the contraption looks even more ridiculous mounted in the radar room. Ice cream machine parts and galley brackets nestled among cutting-edge electronics. If this fries the radar, Morrison mutters, we're all getting court-martialed. At 1800 hours, they power it up. The radar screen flickers, on, off, in irregular pulses. But it works. Contacts appear, fade, reappear. Tracking remains functional. Efficiency at 91%, the radar operator reports, within acceptable parameters. Now comes the real test. For 7 days, the Hendrick operates in the most dangerous waters of the South Pacific. The approaches to Rabaul, where Japanese air patrols hunt constantly. Day 1, April 4th. Radar active for 12 hours. No enemy contact. Could be luck. Day 2, April 5th. 16 hours of radar operations. One Japanese patrol flies within 30 miles, but doesn't alter course toward them. The enemy usually detects radar emissions at 40 miles. Day 3, April 6th. The test. At AZO 200 hours, a formation of Betty bombers crosses within 25 miles. The Hendrick's radar is operating. Every man on the ship holds his breath. The bombers continue on their original heading. They don't turn toward the destroyer. They don't see them. It's working, Hayes whispers. Son of a bitch, it's actually working. Day 4 to 7. The Hendrick operates radar freely. Something no American destroyer has dared do in contested waters for months. 0 enemy responses. 0 attacks. On April 11th, Hayes sends his report to Admiral Mitcher. EFM-17 operational. Enemy detection avoidance. 100% effective over 7 days, 43 hours of radar operation. Request Fleetwide implementation. Mitcher's response comes back in 4 hours. Approved. Manufacture 150 units immediately. By April 30th, 47 destroyers and cruisers have Walt's device installed. The results are immediate and dramatic. Statistical comparison. March vs. May, 1944. Ships lost to radar-directed attacks. March, 7. May 0, radar operational hours in contested waters. March, average 4.2 hours per ship. May, average 18.7 hours. Enemy aircraft successfully tracking radar emissions. March, 89%. May, 12%. Walt's ice cream machine clutch had accomplished what $3.7 million in Navy research couldn't. June 15th, 1944. 0230 hours. Philippines Sea, Battle of the Marianas. Lieutenant James Jimmy Caldwell pilots an F-6F Hellcat off the USS Hornet. Below, the invasion of Saipan is underway. Above, 400 Japanese aircraft are inbound, the largest carrier strike since Midway. But this time, something is different. Every American ship has radar running continuously. No one's turning it off to hide. The fleet's combat information centers track every enemy aircraft from 70 miles out. They can't find us. Caldwell hears the radio chatter from the destroyers below. They're wandering. They can't track our position. The Japanese pilots, expecting to home in on American radar emissions, find nothing. They scatter. They search. They waste fuel. and the American fighters, guided by perfect radar vectors, massacre them. By the end of the day, a day that will be remembered as the Great Marianas Turkey Shoot. The score is devastating. U.S. aircraft losses, 29 Japanese aircraft losses, 346 American ships sunk. Zero Commander Caldwell will later write, "We had perfect situational awareness. Every bogey was tracked. Every vector was precise. It wasn't a battle. It was a slaughter. And it was possible because our ships could run radar without fear." From a captured Japanese pilot, interrogated June 17th. "We expected to find the American fleet by their radar signals, as we always had. But there was nothing. Just fragments. Ghosts. We could not locate them. We flew until our fuel was gone, searching for phantoms." The strategic impact was incalculable. With radar operating freely, American task forces could detect enemy aircraft 40% earlier, vector fighters with 90% more accuracy, maintain air defense coverage 24 hours per day, operate in contested waters without tactical disadvantage. By September 1944, every major U.S. Navy vessel in the Pacific had EFM-17 installed. Estimated lives saved by earlier enemy detection and improved air defense: 1,147 American sailors and airmen through the end of the war. But the story doesn't end there. Walt's simple mechanical interrupter introduced a concept that would revolutionize electronic warfare: emission control through irregular timing. Post-war analysis showed his device reduced enemy detection probability by 87%. But more importantly, it proved that countermeasures didn't need to be sophisticated. They needed to be unexpected. By 1946, the Navy had replaced Walt's crude mechanical system with electronic timers, but the principle remained identical. By 1952, all NATO forces used interrupted continuous wave radar modes as standard doctrine. Today, every naval vessel, every military aircraft, every modern radar system uses a descendant of Walt's idea: low probability of intercept (LPI) radar, which fragments and varies transmissions to avoid detection. The ANSPY-6 radar on the Navy's newest destroyers? It uses frequency hopping and power modulation, sophisticated versions of what a cook figured out with an ice cream machine spring. Before we finish this story, I need to ask you something important. Now, the final chapter. What happened to the cook who changed naval warfare? Walter Kowalski never wanted fame. After the war, the Navy tried to give him awards. He declined. They offered to promote him to officer. He said no thanks. A journalist from Life magazine wanted to do a feature story. "I just fix things," Walt said. "That's all. I'm a cook." He was discharged in October 1945 and went home to Pittsburgh. Married his sweetheart, Helen. Opened a diner on Penn Avenue, Kowalski's Kitchen. Made the best pierogi in Polish Hill. Never talked about the war, unless pressed. His Navy file records the facts. Devices manufactured based on EFM-17 design. One-way 247 units. Ships equipped. 312 vessels by war's end. Official commendations. Navy Commendation Medal. Letter of appreciation from Admiral Nimitz Patent. Filed none. The Navy tried. Walt refused. Post-war compensation for invention. $0. Walt never claimed it. In 1952, a young electronics engineer named Theodore Hansen visited the diner. He was working on radar systems for the new generation of destroyers. "Mr. Kowalski," Hansen said, "I read about your device in my Navy training. I just wanted to say thank you. The work we're doing now, it's all built on what you started." Walt served him coffee. "You want pie with that?" That's who he was. In 1967, Commander James Caldwell, the Hellcat pilot from the Marianas, tracked Walt down. He brought 14 other pilots with him. They stood in Kowalski's kitchen, these fighter aces, and Caldwell said, "Mr. Kowalski, We're alive because you gave our ships radar they could actually use. Because of you, we came home. Because of you, our kids have fathers. We just wanted you to know, Walt cried. Then he served them all pie. On the house. He died on November 8, 1997, at age 79. The obituary in the Pittsburgh Post-Gazette mentioned he was a Navy veteran and beloved diner owner. Nothing about radar. Nothing about saving almost 2,000 lives. That's how he wanted it. The moral of Walter Kowalski's story isn't about technology. It's about perspective. The Navy's best engineers saw an impossible problem that required a revolutionary solution. Walt saw a timing mechanism that needed adjustment. They saw regulations and protocols. He saw sailors dying and thought, maybe I can help. Sometimes expertise blinds us to simple solutions. Sometimes the person without formal training sees what the expert misses. Sometimes the cook saves the fleet. Today, when Navy electronics warfare officers learn about low probability of intercept radar, some instructors still tell them, this started with a guy who made ice cream and thought differently. Walter Kowalski proved that innovation isn't about credentials. It's about courage. The courage to say, I have an idea, even when you're not supposed to be the one with ideas. The courage to try when everyone says it's impossible. The courage to fix things, even when the problem isn't your job. And sometimes, not always, but sometimes, that courage changes everything.